This will be our last lecture on random walks, and we're going to introduce a new model called an unrestricted random walk. And then we're going to explore that model with some new tools that we haven't used yet that are based on generating functions. So let's just first introduce the new model. It goes again by the name of unrestricted random walk. And the idea here is that the state space is all of the integers. So we'll say S is equal to all of the integers. That was pretty badly written. There, better. The state space is all of the integers, so from minus infinity to infinity. And the structure of the model is going to be like this. We're going to suppose that the initial place that you start, the initial state that you start in, is always going to be called 0. That's where we'll start. And for any time past the initial point, we say that x of t greater than 0. This is going to be equal to whatever it was at the previous step plus a random number z, which is the same structure that we've been using before. And the idea here is that z is again plus or minus 1, so it's 1 with probability p, and minus 1 with probability q, so that at every step you do move either to the left or to the right in state space, but there's no boundary, so you can go on forever. This is going to introduce a couple of issues for us with notation. So we won't be able to force our state space to look like 1 and higher. And instead, we're going to, so since we start out at 0, that's going to be kind of a special place for us in this infinite space. But so let's draw the directed graph. So this is going to be where we start, state 0. So you'll see that when we start to try to describe transitioning between the states, we can still use a transition probability matrix, but it'll be difficult. You wouldn't really be able to write it down in any normal sense. There's no limits to it, so it's sort of an infinite matrix. But so if z is 1 on the first time step, then you advance to state 1 with probability p. That can happen, and so on. And you could go to 2 from 1 like this. You could go back from 2 to 1 with probability q. So all these states are the same. They're all linked together. So minus 1 is over here. And so I think you should be able to see from this that this is going to be an irreducible chain. Every state is accessible from every other one. Now you could, if you wanted to, you could try to force this into the context of gambling, I guess, like I was alluding to. And I suppose the description here is that it's like Gambler's Ruin. You move one step to the left or to the right on that graph at every time step. But it's like gambling with a credit card or with a big debt or credit ability. But yeah, you could also describe motion in one dimension in a discrete space. There's lots of different applications of it. But so this is the unrestricted random walk. All right, so now we're going to introduce some new tools that we'll use to explore this model. So they're going to be based on generating functions, so we may as well just call them new generating function tools, or new generating functions. And we're going to introduce two of them. And they're gonna be based on these two quantities that we've seen before, the n-step transition probability matrix. So I'll just remind you what that is. So we're going to be using this quantity, Pij of n. And so this is the probability of going from state I to state j in n steps. So in other words, the probability that xn is equal to j, given that x0 was equal to I, right? So that's the n-step transition probability matrix. And we're also going to be using the first passage probability, so which we've seen both of these things before, but so this is Fij, and it's a function of n as well. And so this is the thing that is the probability of going from state I to state j in exactly n steps without ever meeting state j along the way. So in other words, it looks like this. So it's the probability, we've seen this before, just reminding you, that x1 is not equal to j, and x2 is not equal to j, and so on up to xn, which is equal to j. So I guess you could write this xn minus 1 is not equal to j, and then xn is equal to j, given that x0 is equal to I. Just fits on there. Maybe not, actually. I'll move this over a bit. Right? So we're going to be using both of these quantities that we've seen before, but I just kind of wanted to remind you of what these were. The n-step transition probability matrix and the first passage probability. Now, so the thing that we're going to introduce look like this. So the first one is going to be a generating function based on the n-step transition probability matrix. And for that, I'm going to give it a sort of a maybe slightly dangerous notation. We'll call it P, but with indices. So this is not the normal, like just probability. I'm putting indices on it. It's a function of S, and it looks like this. So it's a sum n equals 0 to infinity of S to the n times Pij evaluated at n. All right? So we'll talk about that in a second. And the other one we're going to introduce is exactly the same kind of quantity, but for f. And so we'll use this notation for it, Fij of s. So each of these is a generating function. Now here, you can't really start the sum for f at 0, so I'll leave that aside for a second. So it's going to look like this. S to the n, and then Fij evaluated at n. If you think about this, if you look at that definition for f, for Fij of n, if you try to put n equals 0 in there, it says that's the probability of going from I to j in 0 steps. Or in other words, it's the probability that x0 is equal to I. The probability that x0 is equal to j, given that x0 is equal to I, which is always 0, except in the case where I is equal to j. So it's a little bit of a funny quantity that doesn't really work right for us. And so we're just going to say this sum goes from 1 to infinity. And so we're going to use these two generating functions to do various things to kind of explore our new model. But I want to point out right away, these are not necessarily probability generating functions. These are not always probability generating functions. They can be, and maybe in a lot of contexts they are, but they don't have to be. And so we don't want to use that name for it necessarily. The rules for this to be a probability generating function are like this. So we would need the following for both f and j. These are the rules for these to be probability generating functions. We would need that when you sum them all up, we'd need this to be 1, and we would need the following. We'd need this to be true. And you could put f here as well instead of p. We would need these things to be true if these are going to be probability generating functions. And this one here on the left is not always true. So this is not always true. This one over here is true, always. It's always true because both Pij and Fij are probabilities. But it isn't the case that if you sum up all of these n's for going the probability, like say from going from state I to j in n steps, that you get 1. It could be that j is not accessible from I, in which case you get 0. So that first term, that first condition is not always met, but the second condition is always met, both for p and for f. But this isn't really important. This is just like whether or not you're allowed to call it a probability generating function as far as we're concerned, and whether or not you could use these quantities as probability mass functions and then kind of use some of the rules that we saw before for expected values and stuff like that. So it's not super important for us. It's a little bit pedantic to worry about whether or not they can be called probability generating functions. But yeah, I just want to point out that they are not always probability generating functions. Now we're going to restrict ourselves to talking about where you can go after starting at state 0. That's kind of the topic of interest for this model. And so because of that, we're going to introduce kind of a shorthand notation that works well for our model. So for our model, and by that I mean the unrestricted random walk, we'll always have I equals 0. So we're going to use a shorthand notation for these quantities, and it looks like this. So we're going to say that Pij of n, that's a quantity we kind of know about, that we're only going to be interested in the following, P0j n. That's the only one we're going to use. And so we're going to define this to be Pj of n, because we're never going to play around with that first index. And so we'll just introduce this new symbol. And so therefore this is the probability that xn is equal to j. And you could put here, given that x0 was equal to 0, and that's correct, but we are always going to have this, and so it's for our discussion. So we're just going to eliminate that part of this. We're not going to consider transitions from any other place. So we're just going to move this, and this is what our shorthand notation means. And similarly, we're going to introduce a shorthand notation for f. And so this also means the following. So for the generating function Pij, we can have a shorthand notation as well. So we're going to say this is always for us going to be P0j, and we're just going to name that Pj. And we're going to do all these same things for f as well. Oh man, writing is a mess today. All right, so we'll also use Fij. We're always going to look at 0, oops, j. We'll always take that initial state to be 0, and so this we'll just call fj of n, and similar. So lastly, we're going to introduce fij for the generating function, and that's meant to be an s. Man, my writing is a mess today. And so we'll just call this f with one indice. Now we'll introduce a property that relates these two generating functions to each other. It's an important one that we're going to use in future proofs, but I'm going to skip the proof of this particular proposition. But so let's write it out here. And I'm going to start by writing it in terms of any I and j, and then I'll show it how it looks in our shorthand notation. But so the idea is the following, that the generating function for p, its elements are related to the generating function for f in the following way. So there's a Kronecker delta, which is either 0 or 1. I'll define that in just 1 second in case you haven't seen it before. And then plus fij of s times p jj of s. Right? So that's the proposition. Oh, and I forgot I was going to tell you what this guy is. So in case you've not seen it before, this is used a lot, the Kronecker delta. It's sort of like the identity matrix, except it doesn't have any boundaries. It's 1 if I and j are the same, and it's 0 otherwise. Okay. So again, this is a proposition that we're not going to prove. The proof is in your notes, though, and it's kind of a fun one. You sort of imagine going from one state to another and talk about stopping somewhere, visiting one of the states. I forgot how it goes. You go from I to j with one stop somewhere else, and what is the time that stop happens at. It's kind of fun. But the proof's a little bit long, and we're only really going to use this proposition for this one thing, and so it's not going to be an examinable proof. So in the shorthand notation, in our context, in our model, or for our model, I should say, this just translates into the following. So we lose an index. We basically put I equals 0 everywhere. And for the p and the f, we delete the I. So this term is 0 unless j is actually equal to 0. And this guy keeps both indices. Okay. Now again, so the proof is in the notes. And it's not examinable. But it's kind of a fun proof. You might like looking at it. So we're now going to finish off the unrestricted random walk problem by trying to prove two different things. And so the first thing we're going to try to prove, it's listed in your notes as like a 3-part proposition, but it's really only got one part to it. And so it looks like this. So proposition. And so we'll write out the 3 parts. The first part says that P0 of S is equal to 1 plus F0 of S times P0 of S. I think I've got those in the opposite order from what you have them in your notes. But this one is trivial. You just put J equals 0 in the previous theorem. So this one is trivial. so I won't really bother with that. 2 is the one we'll focus on, and that one says that P0 of S and it gives an actual expression for it. It's the quantity 1 minus 4 times P times Q times S squared, all square root. Minus to the minus 1/2. So 1 over the square root of all this. Right? So that's the one that we'll spend most of our time on here in this, the proof that we're about to do. And the third part of this proposition sort of follows from 1 and 2. It just says that F0 of S is equal to 1 minus the quantity 1 minus 4 times P times Q times S squared, all to the 1/2. Right, now, I really don't want to spend much time, so 3, this one follows from 1 and 2. If we figure out 2, that if we show that the second part of this proposition is true, you substitute that into the line that's in part 1, and then you solve for f sub 0, and that gives you this result. So I'm not going to bother with that. It's just simple algebra. But so we'll look at the proof of 2. Which in essence is going to prove the whole proposition for us. So this proof is kind of fun. It works like this. So the first thing we're going to do is think about the following thing. So notice the following kind of interesting fact. So notice that if you're going to have, so if x0 is 0, which is true for us, that's part of our model, and if you're, then it must be the case that x with a time index which is odd, so 2m plus 1, where m is an integer, this can never be 0, right? So this state, you can never be back at state 0. So this is for m is equal to, 0, 1, 2, and so on. You can never get back to state 0 in an odd number of steps. If you started at state 0, so the whole point of this proof is we're trying to figure out something to do with the probability of going from state 0 to state 0. That's what's going on here. That's a generating function for that quantity. So we're interested in this going from state 0 to state 0. And if you start off at state 0, you have to take an even number of steps to return to state 0. Sorry, I should have written that. And so it's never going to be the case that x sub 2m plus 1 is equal to 0, because that will be an odd number of steps, right? Also, another kind of cool trick is that if you've got, so suppose you've got an even numbered index, and suppose it's landed back at 0. So suppose you have 2m, x sub 2m equaling 0. So you've come to state 0 again after 2m steps. Then it has to be the case that half of the steps were positive and half of the steps were negative. In other words, half of the steps went to the right and half of the steps went to the left on the directed graph. So half of these guys, z sub i's, are 1 and half are minus 1. And so we can kind of piece together what is this probability then, just by thinking of all the different ways that you can do this. So we'll say this, so this is like a combinatorics thing. So we'll say the probability of having x sub 2m equal to 0, right? So you've got m steps, m positive steps. So you've gone through 2m time steps. M of them were to the right, and so that's going to be p to the m. and m of them were to the left, so q sub m, right? But there's a lot of different ways to do this, different orderings, right? You could go all to the right and then all to the left, or you could do it in different orders. And so there's a binomial coefficient here, 2m and m, right? And so just a reminder for you, if it's been a while, this guy, in words, it's like the number of arrangements for the m plus 1s in the 2m trials. All right, and the formula for this is just 2m factorial over m factorial times 2m minus m factorial. All right, now that's most of the work, just figuring out this little clever trick. So now we'll do the following. So we'll try to write out the left-hand side, the thing we're after. So then, here's what we've got. We've got P0s, right? So we'll just put in the definition here. So this is the sum as n equals infinity, or 0 to infinity, of little p 0 n times s to the n. Now remember, this is just suppressing the first index. So that little p means the probability from going from state 0 to state 0 in n steps. And so now I can just substitute in that thing that we just figured out. So this thing here, we get that from here, right? But so remember, so a lot of the n's don't contribute because they'd be odd numbers. So we only keep the even numbers. And here's what we get. So you can just write the even numbers. So we'll say m is 0 to infinity. And then we'll say P0 2m of 2m times s to the 2m, right? Since odds don't contribute. And now we put in our result, right? So this is precisely our result right here. This actually is this quantity, right? And so I might just take it and we'll put it in here. And then we've got s to the 2m, right? So in other words, let's just rewrite this. We could just lump all those p's, q, and s together, except s gets a factor of 2. Should have just written them out. Silly moving things around. Okay, now the last part of this to realize, so this turns out is equal to, so let me rephrase. So now, by comparison, there's two ways to see this that I know of. One of them I kind of understand, the other one's a bit shady to me. By comparison, you look at the following. So you can look at this thing, 1 minus x to the minus 1/2, right? So that you can look at that, look at the Taylor series for that, and it looks like this. Right? So you could work that out. So you can, and then what you want to do is you want to compare this sum here to this sum here to try to work out the form of this quantity here. The alternative is you can look at something called the generalized binomial theorem, but I'm going to not really delve into that. You find the following thing that you were after. And so I'm kind of leaving out the key last step here, but it's a straightforward one, I think. like that. And that's the proof. Okay, let's take a step back for a second and sort of look at what we've done. So we found P0. So this proposition, if we go back to see what we found both P0 and F0, the generating functions. The heart of that proof was proving line 2 there. But we've got both P0 and F0. And why are we focusing on this state 0? You might wonder. I don't know. But the idea is that all the states are the same. And so you can just focus entirely on one state. Or you could say you start the problem at any one moment and declare the state that you're working in state 0. But they're all in the same communicating class. It's an irreducible chain. And so you can just focus entirely on one state, which is what we're doing. So you only need to know these generating functions for one particular state. And that's all that's really of interest, at least in principle. So now I want to kind of work on one last thing that we're going to prove here, which is a corollary to the previous proof. And it says it's got two pieces to it. So it says the following. It says, so suppose, just like we've been doing, that x0 is 0, or declare the state that you're starting from 0, or whatever. And we want to look at the probability that you'll ever come back to this state. So the probability of ever returning is the following. So it looks like this. So we call that, we'll introduce this notation f sub 0. So that's like what we were calling before f sub 0, 0, I think. And so that's just going to be a sum over all the probabilities of returning in any number of steps. Right? And the claim that we'll prove is that this has three possible results. So first of all, so it has to do with what is P and Q, how they're related. So if P and Q are the same, so in other words, if it's evenly matched, then this number is 1. Right? So if it's a sort of a fair game, or if it's a random walk and there's equal chance of going left or right, or up or down, or whatever your one dimension is, then you will return to the state that you start from if you wait long enough. But if it's not, if there's some bias, I don't know if that's quite the right word, but if P is greater than Q, which means it's more likely to advance to the right, say, then this is 2P. Oh, sorry, 2Q, right? And if P is less than Q, then it's 2P. And so for these three different conditions, one of them is what we call a recurrent state, right? That's the kind of state where you're guaranteed to come back. And so that happens if it's equal chance of moving to the left and to the right. And that sort of makes sense, right? So if you're doing an unrestricted random walk, and there's a bit of a push to one side, it sort of seems sensible that you'll never come back from where you started. And if it's equal chance of going either way, it seems sensible that you'll come back. So that's the first part of this corollary. And the second part is that if, in that case, if P is equal to Q, the states are actually null recurrent. So all the states are the same. This is all the states are the same anyways. Null recurrent. Right? And what that means is that the expected amount of time it takes for you to return is infinite. Right? All right, so let's work on the proof. So to do this proof, we're of course going to have to rely on the previous one. So the first part looks like this, right? So we're saying f0, and let's just write out what this guy is. So it's the sum of n equals 1 to infinity of f0 of n, right? But now remember what the generating function we created looks like, right? So that's the one for f looks like this. Fj of s is equal to the sum of over n equals 1 to infinity of s to the n times little fj of n, right? So this thing on the left, f sub 0, that's the same as that sum. This sum is the same as this sum if s is equal to 1, right? And so this guy is equal to f0 evaluated at s equals 1. So if we just go back to our previous proof, where is it? Or proposition. So we're going to take this guy and just put s equals 1. Okay? Okay, so this guy is then the quantity, or sorry, it's 1, oh man. It's 1 minus the quantity 1 minus 4 times p times q, and s is 1, so it's gone, all to the 1/2. All right? Now we just need to do a little bit of algebraic maneuvering, right? So we'll do this in sort of an awkward way, I think, but so note the following thing. I want to rearrange, I want to make a new statement for what is 1 minus 4pq. Maybe this is all old school, boring algebra for you. But you can write this p minus q squared plus 4pq. Right, if you expand that, you get p squared minus 2pq plus q squared plus 4pq, right? And that's equal to p squared plus 2pq plus q squared. And so that's p plus q squared. But p and q, when added together, give 1, right? So this is 1. Okay, so if I clean this up, right? So now if I solve for, so I've got, what I'm trying to do is recognize here's 1 and here's minus 4pq. So I'll move this over to the right-hand side. And what I get is 1 minus 4pq is equal to p minus q squared, right? Therefore, this quantity up here, that's the square root of a perfect square. So we can write this as f0 is then equal to 1 minus the absolute value of p minus q, right? Now it turns out that's going to be the thing we were after, and I can just show it in a second. But so we're going to get this as 2q for p greater than q, and 2p for p less than q, and 1 for p equals q. The last part's obvious. It's definitely 1 if p is equal to q. But for the others, you want to use, you want to eliminate p in favor of q to make that, to see that last part. Right, so that is to say 1 minus p plus q. That's what you get in the case where p is bigger than q, right? And so that's 1 minus, and you can rewrite this as 1 plus q plus q. So that's 2q, right? And you can do a similar thing. If p is smaller than q, then we've got 1 minus q plus p, and that's equal to 1 minus 1 plus p. Oops, go away. And that's 2p. Okay, now we'll work on the second part. And the second part is to show that if P is equal to Q, then state 0, or all the other ones, since they're all in the same communicating class, is null recurrent, right? Now so there's sort of two parts to being null recurrent, right? The first is that you're recurrent. And then is that the second part of that is that the expected time to return is infinite. And so we saw, so the first part is really easy, saw that if P is equal to Q, right, then we've got F0, which is normally F00, is 1. Okay, so if this is true, it means that we can treat the F00 of n as a probability mass function. For the recurrence time. I usually write those as capitals, I think. I don't know why I did that. For the recurrence time. All right. Now let's suppose that t, capital T, so we'll make a random variable, right? So let's say t is the time of first return. Right? So that means the probability that t is equal to n, I guess I should put a subscript of 0 on here, is equal to F0 n, right? Then we could make a generating function for this quantity, right? It's a random variable. Its generating function is, in fact, its probability generating function, I should say, is this guy, right? Which we've just spent time working out. And so we'll write that out. All right. And then the expected value of this random variable is the generating function, its derivative evaluated at s equals 1. Okay, and so we'll take that derivative. Okay, the derivative of 1 is 0, and so we've got minus 1/2 minus 1 minus 4 pq s squared, and then the derivative of the inside, sorry, to the minus 1/2 now, and the derivative of the inside is 8p minus 8p q s. All right, and we want to evaluate this at s equals 1. And so we get, what do we get here? The minuses, the negatives cancel. We get 4pq 1 minus 4pq, and s is equal to 1, so that's to the minus 1/2. Okay, now let's look at this the following. So this is the same thing as, we want to look at the case where p and q are each 1/2, and so that's 4 times 1/2 times 1/2, so that's 1. And so what we're really interested in here is this kind of thing. So the thing looks a little funny then. We want to look at the limit that x is equal to 1 of x over 1 minus x, right? And square root. That's important. And that's infinite. So that's all we're going to say about random walk problems. And I have a minute or so I'm going to do a quick, just a brief kind of preview of what's coming up next. So our next topic is called branching processes. And there's a lot of things that can kind of fit into this this structure that we're going to introduce. And so I will kind of, at the start, just kind of leave it as an arbitrary thing. So suppose that you have some kind of a population. You could maybe think of like a neutron flying around in a nuclear reactor, and it's about to hit something, or maybe hit something, generating more neutrons, say. And so let's represent that over here with this little circle, like a neutron flying around. And let's write on the top here, so this is time step 0, and we have one of these neutrons, right? Now, when the neutron goes and has some sort of a collision or potential collision, it may split off more neutrons, right, from a nucleus or something. So this moves forward and hits some kind of an event, a collision with another particle, say, a nucleus. And off of this comes potentially more, so let's just represent it as, let's suppose that 2 came out, right? And so we'll say that at time step 1, which is this next one down the line here, we've got 2, right? So 2 neutrons now exist. And then these guys fly around, and then each of them has a potential branching. And let's say that this top one doesn't do anything, it just flies along, doesn't make any more. Right, so we'll put another circle here just to represent that. But the bottom one, let's say it flies along and hits a nucleus, and out springs 3 neutrons, like this, right? So for this guy, so each of these things is lined up with the circles. And so here we are at x2, and we've got a population of 4 neutrons now. And then you could have, say, you go forward, these guys have a potential to branch off, but they don't even, they just actually stop entirely. They disappear. And then this other one springs off and makes 2. So each of these little rectangles is a branching event. And this guy, let's say he springs off and also makes 2. Right? And so here we've got x4 is also equal to 4. So the population is the same, even though there were some changes to things, right? So this is the idea, right? So these circles are members of a population. And the little rectangles, these are called branching events. Right? And you can sort of, I think, imagine a lot of different things that might fit into this description. At least I hope so. The original discussion or introduction of this problem, I believe it was the first people who worked on this, was a pair of people called Galton and Watson. And I think maybe we should just sort of ignore them in a way, because I think they were focused on some pretty unsavory questions. I think they were particularly interested in the extinction of fancy surnames, or something like that. But I don't know. It's one of the less, one of the more embarrassing topics from the history of statistics, of which there are quite a few. And in this case, like each of the branching things meant the production of a male heir. But yeah, again, it's pretty unsavory past. But so this is the kind of problem that we're going to deal with, and we'll start talking about that in the next lecture.